All right, line P1, we're taking a look at learning task 10, which is now going to be doing my calculations for my different types of tapped transformers. We saw this illustration in the previous learning task, and we learned that, we have got these transformer taps that are going to go and adjust, ultimately for us, what we refer to as our volts per turn ratio that we are going to go and have off of it. And the way to do so is just off of a percentage rating that we are going to have over here. Now, I'm going to straight up warn you at the beginning of this learning task that a lot of the calculations that are inside of this learning task really are extra. It's not so much that in the field you're going to go and do a lot of these calculations, because they're asking you to go and figure out things like, the transformer number of turns, or the just random things that are going to be different than the way we would calculate in the field. Let's start, before we get ourselves wound up in all of their math that they have, placed inside of here. And it's all been placed in there with best of intentions, that you get familiar with what the actual construction is. Because if you only learn the basics, you don't necessarily understand what's going on inside of it, right? Everybody here hooked up receptacles to 120 volts before really having an idea what was going on with 120 volts, 240 volts in the neutral over there. We are going to go and talk about what happens in the field first, then we will talk about the rest of the turns ratios and calculating the voltages, etc. that they have. Let's start with this very first one over here. So this is our transformer. What we normally do is going to be the exact same as what we talked about in that previous learning task, where we are going to go and take a look at our load. So I've got a load over here. I'm just going to draw it right now as a resistor. That load that is attached to this thing is operating underpowered. Okay? Let's go and say that we have got this thing that is operating at a value of 224 volts. What is it supposed to be operating at? It's supposed to be operating at 240 volts. Now, I'm not necessarily going to go and measure the high voltage side, because for me to go and measure the high voltage side, let's just say that it's brought in over here, right now. If I measure the high voltage side, I'm going to go and have this issue where I need to have a meter that's good for 2.4 kV. I also need to go and have a properly rated, especially rated in the calorie values there, arc flash suit that I would need to be wearing when I would go and take that measurement. So I'm just, generally speaking, not going to be measuring that high voltage side. Instead, I'm going to be looking at this low voltage side. And I see over here it's 224 volts, and I see that I've got to rate it of 240. And so what I'm going to do is I am going to go and just take a percentage out of here. Okay, so what we'll do is we're going to go and take 224, my actual amount that I have, out of my rated 240, which is going to go and get me to a value of 93%. So what I would need to do is I would need to try to move to the tap that is going to be closest to 93%, which would mean that I'm going to power down and reconnect over here. When I do make that reconnection over there, I'm going to go and get a increased amount of voltage out. How much volts? Well, let's go take a look where we were originally. Okay, this is where we were originally, had 224 volts. If I'm at the 100% tap, that would mean that I'm at a 10-to-1 transformer ratio that I'm going to go and have across to this side over here. Which means that if this is 224, this side over here would have to be 22,040 volts. That's now accounting for all of the drops that I have in the lines leading up to this. Distribution, sub-distribution, along, power stingers coming down to the back end of the property where something's built, whatever it is, we've dropped from what we should have had of 2400. That's what my transformer's dream is, that it would be getting 2400, but instead we are feeding it 2240. So we just need to compensate for that. We are then going to go and take it over to this one based on that calculation, right? Our actual divided by our rated. Our actual was 224. My rated was 240, and we found out that we need to get to 93%. We don't have a 93%, we've got a 95%. So instead, we're going to go and move it to the 95%. What does that do to my value of voltage over here? Well, at this point now, it is going to change my transformer volts per turn. Before, I was putting 2240 volts over top of 100% of the turns. I don't know how many turns it is. I can give it a nominal number, let's say 100, and then I would be able to go and calculate that across the other side if I knew the number of turns. Usually what we end up doing, instead of counting the number of turns, is we just refer to our turns ratio. And the next table down there just shows you a calculation of the turns ratio. At 100%, and that was not shown, it should be right here in the very middle of the table over here, we would have a 100% would be a 10-to-1 ratio that we would have. Right now, we are at 95%, which means that we're going to go and take 10, because that's what our 100% ratio is, times 0.95, which gives me a ratio of 9.5 to 1. In other words, my voltage ratio on the low side is going to be 9.5 times smaller than what's on my high side. What do we have on our high side? We've got 2240 volts. We just did the calculations to get ourselves there. Let's find out what that changes to now that we go to this 95% tap. So we are going to go and take 2240 and we will divide it by point. Oops, sorry, that shouldn't have the point there. Divide by 9.5 equals a value of 235 volts. All I did is I took my line in and I divided by my turns ratio. It tells me that now what we would have adjusted this to is, instead of us operating at that super low voltage, we are now going to be at 235.7, so almost 236 volts that we would have. Pretty close to our desired value of 240. This is the way that we calculate it in the field. Now, there is a reason that you do need to understand what the transformer taps are, because this was working off of the assumption that we started at 100% tap. There is some problems sometimes where we could be starting at the 102.5% tap. And if we're starting at the 102.5% tap, we can't necessarily work off of this. Now, once again, the most common thing that you're going to run into is that when you install a transformer, you put it on the 100% tap right away, because that's what the system is designed for. So usually when you come into these situations, you're dealing with that 100% tap and then having to change over to your values of voltage. If we come in on a higher tap, we would need to go and recalculate what we would have for all of our values coming into this one. Let's take a look. We're going to go and work with a new value of voltage just so we don't mix any one. It's going to be close to my other one. And we will go and see what we get over onto the other side. Let's say that at this point, we're working with a value of 226 volts that I have across my load. Now, my load should have a value of 240 volts. We know that because that is the rating of our system. But right now, we're getting 226 volts out of this thing, and when I open up the transformer plate, take a look inside there, I see that this thing is on the 102.5% tap. So what I need to do is I need to go and figure out how many volts do I have incoming over here. Once I know that incoming voltage, then I'm going to be able to go and figure out my percent tap off of it. Here's how we figure out that incoming voltage. I know that I'm at 102.5. which means that my turns ratio is actually 102.5 times 10, which would be, 10.25. So I take my rated turns, 10 to 1. That is what this thing should be, 2400 to 240. I then multiply that 10 to 1 by 102.5, which gets me to 10.25. 10.25. What I can do now is I can just go take this 226, multiply it by 10.25, and that'll tell me exactly what I've got on the incoming side. Let's go and do that. 226 times 10.25, which gets me to a value of 2316.5. So my actual value being fed in is 2316.5. What percent is that of my actual over here? I don't know. We're going to go and find out. My rated, I should say, not my actual. So we're going to take what the actual is, divide it by my rated, 2316, divided by 2400. Which gets me to a value of 96.5%. So I am currently coming in to this transformer at 96.5% over here. Lovely. Now that I know that, I know where I can go and pull my transformer taps to. I should be at the closest to this 96.5%. If I go to a slight bit higher, 97.5%, I'm still going to come in a little bit low. If I go to a little bit lower, then I'm going to come in a little bit high on this side. Generally speaking, it is better to be a slight bit low than it is to be a slight bit high. So I'm going to go and take my tap, and I'm going to move that tap over to there, to the 97.5%. And at that point, I would now, once again, recalculate to figure out what I'm going to go and change this to. If I'm at the 97.5%, that means that my turns ratio is actually 9.75 to 1, which means that this voltage that I'm going to go and see on this side is going to be 9.75 times smaller. So I'm just going to take 2316.5 divided by 9.75. That's going to get me to a value of 237.6 volts. So by moving down to here, we get rid of this 226, we move to 237.5 volts, like that. This is the way that in the field we do most of our calculations. What we're always going to be doing is we are going to be looking, figuring out what is my incoming line value of voltage. Once I know what my incoming line value of voltage is, I then just need to go and find out what percent that is going to go and be and move to the closest tap. Generally speaking, we go to the slightly higher tap so that our output voltage is slightly lower than rated. If I would have gone to this 95% tap, I would have ended up at about 244-ish volts that I would have had. Nothing that's crazy critical, but nothing that's healthy either for our components. Okay, let's go through these questions that they have over here. First example that they have is what voltage occurs across the secondary terminals of the transformer in figure 1 if the primary voltage of 2300 volts is applied to the 95% tap. So we can go and take this, and we can apply 2300. Well, if it's at the 95% tap, that means that my ratio is 9.5 to 1. So take 2300 divided by 9.5. Gets me out to a value of 242 volts off of that one. Slightly different calculation method than what they go through. They've got more math written out, but this is just as correct. What's our voltage? And then if I know what my ratio is, this one should be 9.5 times smaller over here. Example number 2. What voltage would I need to go and apply to the 102.5% of tap of the transformer in order to produce a secondary voltage of 240? This is a backwards type of question that I'm going to go and have over here because we don't pick the voltage. We have a voltage. Okay, there's line drop that's already happened and has brought us to this point. So we have a voltage, but whatever. We can humor them and we'll work through this thing backwards over here. If I need to go and produce a secondary voltage of 240 from the 102.5% tap, so from here to here, what I'm going to need to do is just go and figure out what that multiplier would be. Once again, if I'm at 102.5% tap times 10 to 1 gets me to a 10.25. So 240, I can just multiply it by 10.25. Gets me to 2460. If you take a look at that, 2460 over here is just going to be a little bit higher than the rated of 2400. That makes sense, the way that they've got that one laid out. Poorly worded question because, once again, we have an existing voltage and we always adapt to the existing voltage, not that we have a transformer and we force the voltage to adapt to that. That's backwards thinking. Example number 3, which tap was used on the transformer in figure number 1 if a primary voltage of 2350, so I've got 2350 coming in, applied produces a voltage of 241 on this side over here? I don't know, but we could just go and take 2350 divided by 241, and then it is going to go and tell us what this ratio would go and be. 2350 divided by 241 is equal to a 9.75 to 1 ratio. So therefore, if it's a 9.75 to 1 ratio, we would have had to have been using our 97.5% tap over there. Example number 4, what is the turns ratio of a transformer when a primary voltage of 600 volts, I didn't have that one there. What is the turns ratio of a transformer when a primary voltage of 600 volts applied to 105% tap produces a secondary voltage of 457? What we need to do is we just need to go and find out what we have at this point at that 105%. So if I go 600 divided by 457, that's going to go and tell me that currently I am getting 1.31. And that 1.31 is at 105%. So all I need to do then is just divide this 1.31 by that 105, which is going to go and tell me that the actual rating of that transformer is going to go and be at 1.25. That would be the 100% rating, would be at 1.25. Once again, is this a useful calculation? Absolutely not. The useful calculations were the calculation that I went over with you over here at the beginning, before we went into, their couple of calculations that they had inside of here. Because usually what we're doing is we are seeing a low voltage that is existing on our secondary, and our customer is asking us to go and correct that. We haven't talked yet about fault current. We will talk about fault current later on, but on our large transformers, we will go and cut out the center part of our winding. And this is just going to be there for a fault control thing. Fault current is going to be a massive amount of current that flows anytime that my secondary gets completely shorted out. So if something were to happen, a wrench gets dropped across bus bars over there, that would then go and cause a massive amount of current to go and flow on the secondary side, which would go and cause a massive amount of current to go and flow on my primary side over here as well. And so what we want to have is we want to go and have these taps taken out of the center, so we've got fewer components that are going to go and be involved inside of it. The other thing that it allows for, and that they don't really talk about much inside of the book, is for the physics of a fault current. What happens during a large fault current? Well, we're going to get massive amounts of magnetic force as well as massive amounts of thermal force, right? Heat expansion. And so by cutting this out inside of the center, we allow a shorter section of winding to move, to expand towards the center, as well as a larger section over here. What they'll do is they will go and have these final taps that are going to be taken out of the center over here. And then what I can do is I can go and apply always, always, always to my H1 and H2. It's common that we're going to not want to move those ones, and instead we are going to go and just have jumpers that are going to go from section to section that we are going to go and have. My 100% tap over here is going to go and be C to D in the case that they're showing us over here, and then I'm going to be able to go and jump smaller ones, down from the next to the next to the next as we go across these. If that is something that we are at all, concerned about having to change those taps. What they show you on this table, by the way, showing that, C to D is the 100%, is probably more uncommon than it is common. What would be more common for us to have is going to be a transformer that is going to have B to E as being the rated 100%. H1, H2 are still there. B to E is usually going to go and be my 100% tap across there. And then what I will have is then I can go and increase the number of turns by taking this and moving this thing over, so it would be C to E. Or I could go and even increase the number of turns even more by moving it C to D. This would allow me to go up into the 102, 105% that I would be able to go and move up there if I was using B to E as my 100%. If I had B to E as my 100%, I could also take out turns, and by taking out turns, then I would go to more volts per turn. So I take that one out, I would have fewer turns, therefore more volts per turn, so that would start to increase my amount of voltage. Same with this one over here, I could go and then go across from here to here, which is going to go and take out another further 2.5% out of these ones. So it's a chart that works with what was drawn inside of here. somebody put this thing together, I would, in a lot of cases, see that instead of us starting at 95% and dropping down by 5% and then going up to 100%, it would be more common that this would be your 100, that this would be your 102.5, this would be your 105%, and this, excuse me, would be your 97.5, and this would be your 95% tap over there. It's potato though. You know, this was just drawn to go a match to what this one is. In real practice, you're probably going to have 100% tap that is going to be in the middle, and then we're able to range a little bit high as well as range a little bit low. All right, that covers us off on these taps. We're going to go and take a look next at auto transformers.